It's about 30 seconds early, but forgive me. Test 2, I will return it today. I graded them this weekend. And for both sections of the 840 section and the 1040 section, the median grade for everybody from both sections was an 82. Very happy with that. Okay, I mean, sometimes teachers just hope for a 75 as a median grade, but an 82 is great, which means half of the students that are taking 107 with me right now got an 82 or better, and half got below 82. So that's the middle grade. Tomorrow is advising day, and a lot of students just say, day off, no problem, not going to GCC. But it's a great opportunity for you to meet with your advisor without everything else going on. We don't have classes scheduled for tomorrow. We're sitting in our office just waiting for you to come and give you answer whatever questions you have. Maybe look, if you're interested in transferring, look at different transfer institutes and what requirements they have. I mean, this is really a kind of one-on-one time just devoted to you. And the other really good thing is you can sign up for those classes that tend to get filled very quickly right away. So take advantage of the fact that if you come here tomorrow, you're pretty much going to get the pick of whatever you want. Okay, especially if some of your sections now, some of the courses you want to take have just one section that's being offered. Like there are some really popular courses, especially to fill like your literature, for example, your literature requirement. And those get filled pretty quickly. So it's a great chance. And I have a sign-up sheet on my door. I know that at least one of you is my advisee that's in this class right now. You just go in and fill up. I would say if it's the first time we're meeting, put in an hour session, put your names in 2 half-hour blocks. But the other really good thing is if you're still having some trouble with this material, you can put your name into any of those blocks. I have like 9 days, or actually 8, because next Tuesday is Veterans Day. There's no classes. I have 8 days with tons of time just sitting there waiting for someone to put their name in. So if you get your exam back today and you didn't do as well as you wanted, and you want to just sit with me and we'll go over it, and then I can give you like an old test from like a year or two ago, and you can practice it again and see what is there and what still needs to be worked on, because all this stuff you'll see again at some level for your final. So take advantage of the fact that lots of time's available for any of your teachers, not just me, that you can go and see them. Okay, any questions on advising day? I know that, and if you have any questions like who your advisor is, I can help you figure that out right after class as well. Okay, any questions? Okay, so we're going to start polynomials today. Actually, we've started polynomials. We just haven't officially called them polynomials. We've worked with linear and quadratic functions already. And linear and quadratic functions are a subset of our big class called polynomials. Okay, so these are part of our polynomial functions. So let's take a look. There's some new symbols today, some new language. In fact, I want to tell you what some of the new language is going to be today. Or the 2 main concepts we're going to be covering today. One is called end behavior. That's one of the big concepts that we'll be talking about today with trying to get a quick sketch of a polynomial function. We have to get a hold of this idea called end behavior. And then the other big idea we have to get a hold of is multiplicity. So those are 2 really brand new ideas from many of you. Hopefully we have a sufficient number of examples for you to get the idea of what's going on here with each of these. Today we don't have any group activity. Unfortunately, you're going to have to listen to me and work with me for the whole class. It's a long lecture, but there's a lot of new material to cover. So let's take a look first at how we define a polynomial function. So as I mentioned, we've already looked at linear functions, which we call degree 1 because the highest exponent you see is 1, and we call quadratic functions degree 2 because the highest power you see in a quadratic function is the 2nd power. So we're going to expand this today, and this is the definition for a polynomial function. So why don't you just take a minute or two to just look that over and try to absorb what all those funky symbols mean. I'm going to actually shut off the recording and give you a little bit of time to look at it, and then we'll discuss. learning to read math it really takes practice, and most of you, I mean, let's face it, you were never forced to read math books in high school, and you probably, some of you, I know, I see you reading in the studio, are starting to read math books. So when you read something like this, it can feel a little daunting. But if you try to simplify it at all, then I think if you try to put it into a situation that we're familiar with, like a quadratic function or a linear function, you get to see what some of these symbols mean. So when you look at something like this, is there anything that you really don't get what's going on, or you couldn't understand, or a question that you might have written on your notes that will help me explain what about this is kind of confusing? I mean, I've got an idea, but I'm just curious what you found confusing. Anybody write anything down? Any questions? That Dylan? Degree N. Okay, what that means. Okay. So that's confusing. Okay. Other things? Yep. Will? Yep. Okay, leading coefficient and how you find it. Yep. Other ideas? Anything else that is confusing? So if I asked you any question right now about a polynomial function, the other 20 of you sitting in here, you'd get it right 100%? I would ask you something that's related to this box. You think you'd get 100%? Okay, then do number 2. Except for the two people that had a question, I'll come back to. Do number 2 then. So you have some questions. So when I ask you if things look confusing, what's confusing about this? Now that you've tried a few examples and you had questions. Chris? Yeah. Yeah. Where they go? Okay. So you're not clear on the coefficient and the degree, right? What's the coefficient and what's the degree? Anything else? So Chris is like, where does coefficient belong and degree belong? Okay, anything else?
Yeah, where do you start?
Where do you start? Ah, yeah, where do you start? It's kind of very confusing, isn't it? Anything else? Where do you start? Good question. Yeah, Eliza? What is a coefficient of a quadratic term? Yeah. Anything else? Okay. So I kind of like gave you this fairly I'm sure looks to you a fairly abstract definition, and then I asked you for 3 very specific examples. Okay. So first of all, let's take a look at this definition. When you write a definition for something that's supposed to represent just about any possible type of polynomial you can get, you can't put in specific numbers like 2 or -3. You have to have a way to represent them. So one of the most important things about a polynomial is this definition right here. And let me get out my highlighter. There's actually a few here, but let me just show you this right here. N is a non-negative integer. N is the highest degree, the highest power in our definition here of the polynomial. You see here, N, that's your leading term, your leading power. It's your biggest power. So if we were looking at a linear function, what would be the value of N if it's linear? 1. What if it's quadratic? 2. What if it's cubic? 3. Quartic. Quarters, how many quarters in a buck? 4, so this would be x to the 4th power if it was a quartic function. How about quintic? 5. Sextic. 6, we never talk about sex in math. That's why it's no fun. Anyway, all right. So n is the highest power you see. And what's really neat about polynomials, and they are neat in the sense that it doesn't take a lot of like hard work when you're looking at them and you're trying to figure out the domain, is these numbers n and then maybe one that's one smaller than n and then two smaller than n all the way down to x sub 0. We don't bother writing it in, but I could write right here x to the 0 power. Because what's x to the 0 power? 1. So if I have a sub 0 times 1, it's just a sub 0. We don't have to put in the little x sub 0 there. But the key idea here is that all of your exponents are non-negative integers, which makes them those nice friendly numbers you always think about. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can't have negative integers, which means you don't have any denominators to worry about in terms of your domain. And you can't have fractional integers, which means you have no roots to consider to worry about for your domain. So what makes polynomial functions really nice is the fact that all of the exponents you see are non-negative integers, and the domain for every single polynomial function is all real numbers. There's no head things you have to worry about. You don't have to think about, oh, what's going to make my denominator 0? Oh, I've got an even root, and I've got to figure out what I can't put in there. And they're just really nice things to graph. Right? Now, coefficient is, in our case, we're going to just refer to it as a number, but it could be any factor. But in this case, a coefficient is a number that multiplies x to a power. So notice if our degree is n, in order to say the coefficient that goes with x to the n, we give it the same little label, a subscript n, a sub n. So an minus 1, all the way down to our constant right here, they're all real numbers. So they could be nice integers, they could be irrational numbers, right? But they can't be imaginary numbers. They're all real numbers. You can find them on the real number line. The leading coefficient is the number that multiplies your variable x to the highest power. So it'd be, we usually put it in front, but it could appear anywhere. We usually write the powers in descending order. That's just what we tend to do. So where do you get started? You read your whole thing. It says a polynomial function of degree 5 with 3 terms, leading coefficient of -3, and coefficient of the quadratic term is square root of 2. All right, that's a lot. So the first thing you see is it's a polynomial function, f of x, p of x, h of x, whatever you want, equals 3 terms. That means 3 boxes. 1, 2, 3. That's what terms mean. Now, in between those boxes, to be a term, you could be an addition or a subtraction sign. Doesn't matter. I'm just going to do that. All right. Now, it's degree 5. So what does that tell you? X to what power is going to be the biggest power you see? X to the 5th, right, William? So you put x to the 5th. You could put it in that box or the second box or the third. It doesn't matter. So you've taken care of degree 5. You've taken care of 3 terms. Leading coefficient. So that means the number multiplying x to the 5th. It's like the lead person in a line is -3. So a sub 5, that's how I would denote it using the notation from that box. A sub 5 is -3. It's the coefficient of the term that has x to the 5th power. So the subscript here and the exponent here match. Okay. Now, what is a quadratic term going to look like? What would a quadratic term look like? X to what power? 2. Right, Katie. So there's my quadratic term. Now, Eliza, its coefficient, the number multiplying it, is square root of 2. So I just throw a square root of 2 in there like that. Okay. So that's quadratic term with coefficient square root of 2. You can put anything you want in here, except for it can't be a power bigger than 5. And it can't be a negative power or a fractional power. So you could put like this, -3x if you wanted. You could put a constant in there like, let's see, you could put in 4x to the 4th. It doesn't matter, any term. You could put in -5, just a constant term, whatever you want. The main thing is that when you look across your polynomial, you don't see any exponent bigger than 5. And you only see 3 boxes. Chris?
Why did we decide? We just decided it's quadratic because
I said it right here. It says quadratic term. Okay? I was very specific there. After you have the 5th power, you could have something to the 4th power, the 3rd power, 2nd power, 1st power, or just a constant. You could actually have all of those terms. But I told you we only have 3. One of them is a quadratic. So you know you have an x square in here, and you know you have an x to the 5th. And that's the only restrictions. The other term could be any number, any power, any integer from 5, well, after 5, 4, 3, 2, 1, or 0. Okay. All right, does that help with the first one? All right. So let's take a look at the second one now. Polynomial function of degree 0. So what would be the exponent on my x value? What would be the exponent if it's degree 0? 0. What would be the number in front of it? Did I specify? No. So you got a favorite number? 44. That's my favorite number. So there's my polynomial function of degree 0. And how could I simplify that? What's that the same as? 44, because x to the 0 is 1. So it's just a horizontal line. So this is any horizontal line, because every horizontal line has f of x or y as a constant. The only exception on this is except the x-axis, because we can't have our leading coefficient be 0. That's what our box says, except the x-axis. We can't have f of x cannot equal 0. So we call this a constant function. Another name for this is a constant function, because no matter what x value we put in here, f of x is 44. If we were doing a table, no matter what x value we put in here, my output f of x or y is 44. It never changes. It stays the same. Okay? So that's a constant function. Okay, what about a function that wouldn't be a polynomial? Can anybody give me an example of a function that would not be a polynomial? Katie? Something with a negative power, yep. 2x to the negative 3 would be the same as 2 divided by x cubed. This certainly doesn't have a non-negative integer, because negative 3 is negative. And if you looked at this function, 2 divided by x cubed, your domain couldn't be all real numbers, because x can't be 0. We can't have x equals 0 in the denominator. Okay? So that's the language of polynomial functions. Any questions before we move on to the ideas of end behavior? Anything at all? Okay. So, and I realized in my first class we talked way too much, about stuff, and we didn't get to like the last couple of examples. So I'm going to try to keep this as brief as we can. So take a look at the scatter plot. Read what the axes are and what's going on here. And then I want you to briefly write a little story that describes what's happening in this graph at your seats. Would anybody like to tell me their story that they wrote about the U.S. energy consumption of natural gas over those decades? What you wrote on your paper from looking at the graph? No volunteers? Andy?
Energy consumption has risen in 2000.
Ooh, increase between 1960 and 2000, yep.
With irregularities. It's not a steady rate.
Irregularities, not a steady rate, okay. Okay, anybody want to give me what they wrote? That's fine. Anything else? It almost doubled. So the U.S. consumption of natural gas almost, blah, 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 almost doubled in the 40 years. Yep. Something else? Anything else? If I looked at your papers, I'd see one of those two things. Yeah, Katie? Between 1970 and 1990, it declined. Yep. So those of you who are still having trouble, whenever I ask you, over what intervals is your function increasing or decreasing, remember this graph. Because if I ask you about when does this function decrease, Katie just answered it. And she didn't give the answer in terms of the vertical variable. She was giving you the time period. It's always over your x interval, your horizontal variable, whatever that is. So when you define where this thing has decreased, you would say between 1970 and 1990 over that interval. It's decreasing. Where's it increasing? What intervals is it increasing over? 1960 to 1970, union with 1990 to 2000, right? Okay, so if you're still kind of stuck on that idea of increasing and decreasing what intervals, just remember this example for yourself. All right, because it makes a lot of sense. So if I was trying to model this, would a straight line model that data really well? Why not? Dylan said no. I could get a positive correlation. Well, actually, believe it or not, I know this may be hard to believe. That's not the line of best fit. It's close to the line of best fit. If you put these 5 data points into your calculator and graph them, you're going to get a correlation coefficient of about 0.7. It's not too bad. Not fabulous, but it's not too bad. You could use it for you could have used it for your linear regression project. But why isn't this a good model? What doesn't it capture, and what does it tell us as time goes on that you don't know if is true or not, or in the past? Why wouldn't this be a good model?
It gives you an average rate of change, but it doesn't accurately represent the years between 1970 and 1990 that the energy is declining.
Right, this says that your energy's been increasing at a fairly steady rate over that 40 years. And that's not what this says. This tells us I increased sharply in the first decade, then I decreased for the next, 20 years, and then I increased again. So that certainly doesn't cover that. And the end behavior here, I hope that we're not going to continue. The end behavior means what happens as time continues. Watch my fingers. As 2000 continues this way and this graph continues, it's saying I'm going to continue to increase and increase and increase and increase. And a quadratic's not very helpful either, even though I could maybe draw a quadratic that might kind of capture some of these points here like that. It certainly doesn't describe. This says that I started off at a really high point and I'm going to continue at a really high point, right? The end behavior here goes way up, and so doesn't the beginning behavior as x is decreasing, as our time decreases from like 1980. That doesn't capture it. That's not going to work. Not going to be very good. So no, nothing's going to really capture this. What are we going to look for here? We're going to try to find a curve that we can fit through this data that's smooth. And what do I mean by smooth? It has rounded curves. Think of Botticelli and the Renaissance painting, you know? The idea of beauty there wasn't twiggy, right? It was rounded hips, curvy, right? If you studied art history, all right? So round, smooth curves that are continuous. In other words, if I were to trace the curve, I wouldn't lift my pencil off the paper. There'd be no jumps in my graph. There'd be no holes in my graph, and certainly no sharp corners like an absolute value. Okay, that's a polynomial function. Okay, so what kind of function do you think I could put through there? What would have to be true about it in terms of looking at its graph? How might you, not necessarily, I'm not asking you for the actual equation, but what could you tell me about this function in terms of its sketch? How might you describe it if I were to sketch it? Katie? It would have a minimum and a maximum, a local minimum, a local maximum, or a relative min and a relative max. Why did she say that? Patrick? Right, because as we start here at 1960, we're increasing, and then Patrick says we then start to decrease. So we have a turning point there. It's like a mountain, right? A mountaintop. So I'd have to have some function that would kind of turn around there, and then I'd decrease, and then what would happen? I'd change again from decreasing to increasing, something like that, okay? So you'd have two turning points. Two turning points. Turning points are like these hills and these valleys, or what we've been calling relative maxes and relative mins. So we're trying to find a function that would model this turning behavior, this changing of from increasing to decreasing and then increasing again. And I did this for you. I put this into my calculator, and this is the actual equation I came up with. That's called a cubic regression. We've looked at linear regression, and you could do linear, quadratic, cubic, whatever. So this is like the cubic of best fit, so to speak. It's the best fit cubic model. Okay, so that's the closest you're going to get with any particular curve, and these are the values. You don't have to write this down, folks. I'm never going to ask you about this equation. I'm just trying to show it to you. So the idea of, as Caitlin said, with a relative max and a relative min. Why is she calling these? Oh, never mind. That's review. We don't need to go there. All right, AIDS cases. So the whole point of this scatter plot that I've given you here, where we show the number of years after 1983 along your horizontal axis and the number of AIDS cases. Again, if I try to fit a curve to this, I would come up with this curve right here, this another cubic curve, which you see right here on your lecture notes. How many terms in this? How many terms in this cubic polynomial? How many terms? 4. 1, 2, 3, 4. Eliza, what's the coefficient of my quadratic term? 806. What's the constant term here? Constant term? Negative 49 we call the leader of the pack, right? That's the leading coefficient. What's my constant term? 2503. It's just the number at the end. Or if it wasn't in standard order, it could appear anywhere. But we tend to write them the highest power down to your constant term. All right. So the domain here is 1983 to 1991 inclusive, means I'm including those endpoints. I have an actual data value for 1983, and I have an actual data value for 1991. So the problem here is so much is going on. I mean, in the first 8 or 9 years of the AIDS epidemic in the United States, we didn't know much about it. So the number of AIDS cases soared. It wasn't until about 10 or 11 years later that start educating the populations that were at risk, whether you were a needle user, you were a homosexual, a gay man, or a hemophiliac, or anybody requiring a lot of blood transfusions. When we started to become aware of how people were getting AIDS, then you notice that we started to have a decrease. And then it leveled off for a while, and then we're decreasing again. So finding one model that represents this is a really difficult thing, okay? So if we looked at the first, say, 8 or 9 years after 1983, we could probably find a straight line that would model it very accurately. But it's not going to tell us what happened after that time. So if you put all these values in and you try to find a polynomial, now this may look like a parabola to you, but notice it's not symmetric. So this is just one part of a cubic. It's one part of a cubic. It's like, here's the actual equation right here. So if this continued on, this would start to, over to the left, it would, let's see, what would this look like? So if we were like this, we're a cubic, it would probably come down like that maybe. Would have some lower relative minimum and some relative max. So if we saw the left-hand side of it, it would look something like that. But you can see here that as time goes on, this model, if I go out to the right, and this is what we start to refer to as the far right end behavior. As I go out to the right, this model is going to be projecting that the number of AIDS cases eventually is negative. That's not going to happen. So the model breaks down as I go further out in time. And we've talked about this model breakdown. Will? If you go backwards in time, especially in these earlier years here, the model's going to be pretty darn accurate. Yeah. Oh, back here? Yeah, it's going to break down because at some point it's going to have the number of, if I go down back here, the number of AIDS cases being higher than here. Yeah. Yeah. So you've got to be very specific. The only way what we could do here is maybe restrict our domain to just the years that we had on 83 to 91, and it would be a pretty good fit. But after that, it's starting to break down. So some of the symbolism you're going to see today and we're going to work with looks like this notation right here. As X goes further and further to the right, as X, and the way we read this is X approaches positive infinity. So we read that symbol as X approaches infinity. The value of our function approaches what? What does the value of our function approach? Negative infinity. It means this continues to fall, 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 fall without any cap or bound to it. Okay? It approaches negative infinity. This keeps falling and falling and falling. The language is the graph falls to the right. That's the simple way to say it, that as I move to the right, my graph is falling. So we're going to talk a little bit about this end behavior for graphs that have different degrees. So this is it all in a nutshell for you right here. I have it all in your lecture notes. We're going to cover it fairly quickly. I'm not going to fill in every single little arrow there. But it says the behavior of the graph of a function to the far left, if I turn my back, is as X goes to negative infinity, and the far right as X moves towards positive infinity, is called the end behavior. Okay? So if we start to look at graphs now and we categorize them by their degree, do we notice anything that we see as a pattern? So if you look at all four of these graphs all together, just take a few minutes and look at all four of these. I've got to raise this up and down, but you can see them all at your seats. If you took a minute now and looked at them, I'm going to shut off the recording. Okay, so anybody want to tell me, after looking at these four groups of functions, linear, quadratic, cubic, and quartic, anything at all that you noticed? Any? Yep, Will? Okay, so all graphs either rise or fall. And if you were looking in your book right now, they would tell you that that's true of all polynomial functions. Your end behavior, your polynomial functions will always rise or fall as you go towards either end of the x-axis. They've got to do one or the other. They may do both. They may do both. One end you may rise, one end you may fall, or sometimes you're rising no matter which direction you're going in, or falling no matter which direction you're going. What else did you notice? Katie Woods? Even functions, you mean even degree? Yeah, even degree, yeah. Okay, so the f of x, when you say value of the function, will either go towards positive infinity, or that means they're the same, or it will fall towards negative infinity, regardless of which direction I'm going in. Okay, so if we translate what Katie just said, when you look at your even degree function, so look at your quadratics there and look at your quartics. The arms are going in the same direction, right? No matter which way you move, the arms are going in the same direction. Okay, that's true. Anything else you notice? Yep, Tom? Ooh, that's interesting. Number of, so the maximum number of turning points, right? Maximum number of turning points, oh, that's good, is one less than the degree. How do we refer to the degree in just general notation? What letter do we use for the degree of the polynomial? N. So if we wanted to say one less than that, we'd say n minus 1. Okay, that's good. Wow. Okay. So again here, if we actually just follow our language here, rises to the left. So here's to the left. X is going towards negative infinity. F of x is approaching positive infinity. That's how I translate right here. As x moves to the left, x goes towards negative infinity. The value of my function is increasing without bound. That approaches positive infinity. It falls as I move to the right. So as x goes towards positive infinity, the value of my function approaches negative infinity. Okay. What about when I cross the x-axis here? What can you tell me about my function just before I cross the x-axis and right after I cross the x-axis? What can you tell me about the value of my function with the linear function? What can you tell me about it? All right, well, let me ask you a question here. Let's say this is 1.5 right here where I cross the x-axis. And I ask you for the value of my function when x is less than 1.5. What can you tell me about the value of my function when my x value is less than negative 1/2, less than negative 1/2, 1.5? What can you tell me about the value of my function? It's negative. It's below the x-axis. What happens the minute I take a step to the right of 1.5? What does it become? The value of my function. Positive, right? So at 1.5, I'm at 0. When I go to the right of 1.5, I'm a positive number. When I go to the left of 1.5, I'm a negative number. So at that 0, or the x-intercept, on either side of it, my function has changed the sign from negative to positive. This one, we've gone from being positive to negative. So the function changed sign as it went through the x-axis. What about this one right here with the arms up? As I go to the left of -2 and the right of -2, did the value of my function change from negative to positive? Right here, did the value of my function change? Did I go from above the x-axis to below? No, I stayed exactly the same. All I did was turn around, right? I went from being a decreasing function on what interval? Negative infinity to -2, I was decreasing. And then from -2 to positive infinity, I'm increasing. So I'm just a turning point here. I'm not changing the sign of my function. What about the cubic function? Does it act like the linear function? Does it change sign at the 0? At your x-intercept? Does it change sign? You're below, you're above. You're above, you're below. Changes sign. How many x-intercepts do I have with this quartic here? 1, 2, 3, 4. Right, your highest power is 4, so that's a maximum number of real numbers you can have that are zeros or x-intercepts. And as Tom noticed, you have 1, 2, 3 turning points. All right, so the only thing I wanted you to get out of this was if you're an odd degree polynomial, your graphs have opposite end behavior. We actually noticed some things that's coming up. And then even degree polynomials have the same end behavior. So either both arms are up, both arms are down. All right. Now notice I did something here. I started writing in this notation for linear function, quadratic, cubic. I didn't use the a sub 1s and a sub 3s. I just used the letters a and b. So if we were looking at linear functions here, what do we normally call the coefficient a here? What's the name we normally give to that if it's a linear function? The value of a, what is that normally called? Slope, right? We usually use mx plus b. So what can you tell me about my arms if my slope a here is positive? My right hand arm is up and my left hand arm is down. Yeah, it's going up. It's constantly increasing when it's a linear function. When A is negative, where's my right arm? Down or up? Down. Right? Negative slope. That's all you have to remember, folks. You don't have to remember linear, cubic, fifth degree, 7 degrees. Just remember a straight line. If you have a positive slope, your right arm's up, your left arm's down. If you have a negative slope, your left arm's up, your right arm's down. And guess what? When you now bump yourself up to be a cubic, same is true. This cubic has leading coefficient. A is positive. The right arm is up, the left arm is down, just like with a straight line. And in this one, A is going to be negative because your right arm's down and your left arm's up. So just remember your right arm. If your right arm's down, you're negative. And all you have to remember for your even polynomials is a parabola. And you already know this about a parabola. You know here, if you looked at this, you would tell me that your value for A, your leading coefficient, is positive. It opens upward. And here you would tell me it's negative. So those are really the only two pictures you have to remember. And these two functions are very well known and familiar to you. Because everything else acts the same way. Did I see a hand back there at any point? No? No? Okay. All right. So all of this here that's on your lecture notes, this is from your book. It's a really nice little picture of the arms going in different directions. It gives you all of your language. That's there for you to read. It's a nice little thing to put on a cheat sheet at some point, maybe before test 3. Okay, so let's suppose I never gave you this picture right back here for the aids. In fact, I happen to throw this in at the end. Suppose I didn't give you this picture of the cubic, of this cubic, and I just gave you the polynomial function right here, f of x. Suppose I just gave you that function. Based on what we just talked about, can we think about end behavior of this function and see why this model's not good in the long run? We just saw why, but suppose I just gave you this equation and that was it. What is the sign and degree of the leading coefficient? What's the sign and degree? Well, that's not right. This sign and degree of the leading, all right, the sign of the leading coefficient and degree of the leading term, it should say. Okay. So what's the sign of the leading coefficient? What's the sign of the what is the leading coefficient in this particular model? Sam, do you have lecture notes? Do you want some? What page are we on, folks? Page 8 of class 25. Okay. So what is the leading coefficient up here? Can someone identify what it is? Negative 49 is the leading coefficient, so it's a negative. What degree is this? What's the leading term? The leading term is negative 49 x to the third. That's the whole first term, and it's degree 3. It's odd. So what do you think about right away in your head? You think about a straight line. Forget about the cubic for a minute. A straight line with a negative slope. Where's your right arm going to be? Tell me what to do with my arms if I'm a straight line with negative slope. This or this? Right arm down, right. So this graph is going to have the same end behavior as any odd degree that has a leading coefficient that's negative. So as x goes towards positive infinity, the value of my graph approaches negative infinity. It does not have the same end behavior. As x goes towards negative infinity, the value of my graph, my left arm is up, approaches that. So in the long term, as time goes on, as I move further to the right, my graph decreases. So this is not a good model in the long run to try to model the AIDS epidemic. You can get all of that just from knowing the degree, odd or even, and the leading coefficient. That's what it tells you. That's the information you can glean from it. Okay? All right, so let's move along. Zeros of a function, hopefully we remember from when we first started talking about functions. F of x equals 0. We call the value of x that makes our function equal 0 the zeros of a function. Where do they appear on the graph of the function itself? What do we call them on the graph? X-intercepts, right? X-intercepts. So we're going to find all zeros of this function. So how do I find a 0? I set f of x equal to 0. So where I see f of x, I replace it with a 0. And now I'm trying to solve this equation. This is a polynomial equation, so this takes us way back to section 1.6 that we covered in the first maybe 3 weeks of classes, somewhere in there. It's a polynomial function set equal to 0. How am I going to find the solutions for this particular equation? How am I going to find all the x values that make this 0? Factor out an x. So the first thing I do is look for my GCF. My greatest common friend here is x. I pull that out, and I'm left with x squared minus x minus 2. Thank goodness, that's a nice, easy second degree trinomial to factor. I don't have to use my quadratic formula or anything like that. So I have x minus 2 times x plus 1. Notice you have 3 factors here, 3 different factors. 3 different factors. So how many different x-intercepts are you going to have? 3. You're going to have 3 distinct x-intercepts. And therefore, you will have 3 zeros of the function. 3 zeros of this function. Okay, so how do I find them? I said each one of these factors equal to 0. So the first factor is x. That's all done for me when I set it equal to 0. There's my 0, which is 0, and my x-intercept is the origin, 0, 0. My next 0 here is when x minus 2 equals 0. That's at positive 2. My x-intercept looks like this, 2, 0. And my last factor, x plus 1, is going to equal 0 when x is negative 1. So my x-intercept looks like negative 1, 0. So to verify this, I could pull out my graphing calculator and throw that function in, which hopefully it's still there from my first test. There it is, my first class. So if I take a picture of that, oh yeah, I remember I got to do this first. Let's take a picture of it and throw it in our notes. You can see that the calculator verifies the 3 zeros going through negative 1, 0, and 2. Okay, so those are my 3 zeros. Notice the different names. Zeros of the function, x-intercepts of the graph, solutions to the equation x cubed minus x squared minus 2x equals 0. They all are the same idea with a little bit different twist on the language. So let's examine these 3 graphs and look at the behavior near the 0, near the x-intercept. So we're not looking at the ends anymore. We're not looking at the ends. We're looking at the behavior of the graph near your x-intercept or near the 0 of the function. We know that the parent function for this is x squared, and we've simply shifted it to the right 1 unit, and there's the value for the transformation right here, the quantity x minus 1 squared. Notice x minus 1, the factor x minus 1 appears twice. So if you were setting this equal to 0, you'd write x minus 1 times x minus 1, and you'd only have one solution to this equation, x equals 1. And you only have one x-intercept. So we say that the real, can you hang on 1 minute, Chris, because this is kind of important? If you can, all right? I just don't want you to miss this. All right, so we say that 1, the real 0 located at 1, has a multiplicity of 2. That's brand new for many of you, a multiplicity of 2. What does that mean, a multiplicity of 2? Well, think about 2 and think about this exponent. What it means is that this factor occurs, it's like a double factor, it's a perfect square. It appears twice, and it gives you one x-intercept. located at 1. But the really neat thing about anything with a multiplicity of 2 is when you go to graph your function and you come down and you put your little x-intercept there, you know something about its behavior near there. If you could blow this up, and let's see if I can remember how to blow this up. I don't know if I have that little function here anymore. Probably have to play around with this. If I could blow this up, in other words, I just focused in there, if you could get everything else out of your mind, doesn't that look like a little baby parabola in there? And it is a parabola, right? This is a parabola. But what this says is, at that 0, I don't change the value of my function. I'm a turning point. That's what it says. Whereas if you look at your cubic here and you look at right there, notice your cubic says, if I were to factor this and set this equal to 0 to find my real 0, I don't know, my pen's not working. What did I do? Oh, my pen's not working. Let's try it now. No, it's not good when my pen stops working. Okay, so if I wrote this out on the board, it would be x minus 1 times x minus 1 times x minus 1. My intercept is at 1, 0, and I would say the multiplicity was 3. Okay, notice when you have an even multiplicity, you are at a turning point. When you have an odd multiplicity, your function changes sign. Okay, so the multiplicity of a real 0 tells us about the graph's behavior near the x-intercept. If the multiplicity is even, the graph touches the x-axis at the real 0. And if the multiplicity is odd, the graph crosses the x-axis at that x-intercept, a real 0. Okay, you can go now, Chris, if you need to. I just wanted you to have that information. Okay, so let's examine this polynomial function. Can anybody tell me right now, before we even do any work, is this an odd function or an even, and how do you know right away? Caitlin? You have 3 x-intercepts, which is an odd number, so you can have, well, let's see. I think that's going to be okay. She says 3 x-intercepts, that's an x, so maybe it's an x cubed, huh? At least an x cubed. It could be an x to the 5th or an x to the 7th, all right? 2 turning points, so if we use Tom's idea, 2 turning points, n minus 1 equals 2. I wish I could write. N minus 1 is 2, so that means n minus 1 equals 2. Write that on your paper, so n is 3. And I'm going to try to do a quick orientation here. Let me shut off, I hope I'm recording. Please be recording, yep. Okay, so during class we had a problem with our smartboard, so I'm recording this after class has left. So during class we identified the zeros. We picked each of these x-intercepts, and my pen is still not working, so let me try something else. Hang on. Okay, so I'm going to continue this lecture, even though I don't have my pen to write. I'm going to use the mouse. So I've filled in some of this for you because it's very hard and slow writing with the mouse. So the first question here is to find the zeros of this polynomial and to state whether the multiplicity of each 0 is even or odd. So as a review, an even multiplicity means that at that 0, your function has a turning point. It doesn't change sign. If it's above the x-axis, your function stays above the x-axis. If your function is below the x-axis, it turns at that 0 or x-intercept and it stays below the x-axis. Whereas an odd function will actually cross through your x-axis at that 0 or x-intercept. Your function changes the sign. It goes from above to below the x-axis or vice versa. So let's take a look at the zeros. First, we identify them. They're the x values of our x-intercepts. So we have a -2 for the first 0, a 0 for our second 0, and a +3 for our third 0. Okay, now to examine what's happening right around that 0, let's use our magic pen and let's just blow up right around that particular zero. And let's make this bigger. Oops, let's see. Can I make this bigger? Yes. Oops, I moved it the wrong way. Oops, let's try this again. I haven't practiced with my magic pen for a while, so let me try this again here. If I can find it. Pens, okay. It's not giving me my magic pen back. Let's see, I'll go up here to Insert and View. Where's my magic pen? I bet it's a tool. There it is. There's my magic pen. So let's put a big circle around here, and it's supposed to blow up that area. So let's see what I can do. So if you just look at this area right here and focus on that area, it looks just like a straight line. And so a straight line has a degree of 1. The highest power you see is 1. So we say that this has a multiplicity of 1. Similarly, if we move this to our other zero located at the origin, it still goes straight through the the x equals 0. Notice your function is above, and then below it changes sign. This looks linear as well. And now let's move it over. Ooh, there's how I make it bigger. And now we move it over to 3, and again it goes straight through the straight through the x-intercept. It goes from being negative to positive. So these are all examples of odd multiplicities, and they all have a multiplicity of 1. So that means that the highest exponent you see on any of these factors here is 1. So most of the time we don't bother putting in the 1. Now it's our turn to go ahead and take this polynomial and put it in completely factored form. Okay, so we're going to come down here, and with our regular pen, we'll write each of our factors. Well, if -2 is a real 0, then we know that x plus 2 must be a factor that we set equal to 0, because the solution for this equation is x equals -2. So when I say x take away -2, we can simplify that to be x plus 2. And it's to the first power. Again, I'm just going to write it in for today. Then our next 0 is x take away 0. Right? X take away 0. And then our final factor is x take away 3. So we don't have to worry about any sign changing. We don't have to worry about the subtraction changing to addition unless one of our zeros is a negative number. So right now we could say that a possible equation for this polynomial is f of x equals the leading coefficient here, we're just going to call a for now, times x plus 2, x minus 0, and x minus 3. Again, we could simplify that and say a, and usually x minus 0 we just write as x, and that's usually the first factor we put out there, and then we have x plus 2 and x minus 3. So now the only thing we can do is we can't find the value of a because we don't know any other point on this polynomial function. We could estimate and say maybe 1,4 is a point, but we don't know that for sure. But we can say something about a. We know that a, the leading coefficient, has to be greater than 0. And why do I know that? Because my right arm is up and my left arm is down. My graph rises as I move towards positive infinity, and it falls as I move towards negative infinity. Okay, let's take a look at the next one. The next one is very similar. We notice right away that both of our arms are pointing upward. So this tells us we have an even degree polynomial. So if we had our polynomial written out as a bunch of terms in the form that we looked at the beginning of the hour, then our highest exponent would be even. The highest exponent we see would be even. Okay? So again, we have -3 as a 0, we have -1 as a 0, we have 1 as a 0, and then x equals 3. And now if we take a look at our magic pen and we go right in here and look at the behavior of our function right around the 0. Let's see if we can make that bigger. There we go. Now, if you look right in there, that looks like a parabola, right? Which is an even degree of 2. And this is a situation where our function has a turning point. It doesn't change sign. It's positive here. It goes to 0 at the x-intercept, or the 0 of the function, and then it stays positive. So we say this has an even multiplicity. And because this looks just like a parabola, we say that factor at -3, whose 0 is -3, will have an exponent of 2 on it. So I go over here and I say, okay, at -3, I have an even multiplicity. Where's the other turning point? The other turning point at our 0 occurs right here. That's our other turning point. And that looks like a parabola as well. So at +1, we have an even multiplicity. And if we take a look at both -1 and 3, if I come over here and take a look at 3, the function goes straight through that 0, and therefore it has an odd multiplicity. So when I go down and fill in my equation, I first put in f of x equals, and then a is our leading coefficient. We don't know what that is yet. And we have x plus 3, because x take away a -3 becomes x plus 3. It has this tells me I have 2 factors of x plus 3. I have an even multiplicity. Then x take away a -1 becomes x plus 1. Because I'm going straight through my axis, I just put a 1 for the exponent. And then at 1, it's x take away 1. And again, we have a turning point here, an even multiplicity for an exponent of 2. And then finally at x equals 3 for my 0, I write x take away 3 to the first power. Now you would think that's all we could do. However, we're given a point that's on this particular polynomial function. The point is given to you right here. It says when x is 0, x equals 0, the value of my function at 0, f of 0, is -3. And remember, we call f of 0, another name for that is y. So you can take this point and we can solve now for the value of a and get the full equation for this function. So what I do is everywhere I see an x in this particular function up here, I put a 0. And on the left side, where it says f of x, I'm looking for the value of my function when x is 0. I know that's -3 because that's what this point tells me. So this gives me -3 equals, and remember I'm solving for a. So what's this first factor? 0 plus 3 is 3 squared, that's a 9. The second factor is 0 plus 1, which is 1. 1 to the first power is 1. And then I have 0 take away 1, which is -1. And when I square that, I get a 1. And then finally, oops, I forgot to put my last one in here, 0 take away 3. And 0 take away 3 is a -3. So what do I have on the right side? I have 9 times 1 times 1 times -3, which is a -27a. And when I divide both sides of my equation by -27, I get 1/9 over here equals a. And then I can now write my polynomial function with everything that I need. My leading coefficient is 1/9. My first factor is x plus 3 square. My second factor is x plus 1 to the first power. I'm not going to put the 1 in. And then x take away 1 square. And then x take away 3. Okay. So now we'll end it here for today, and we'll pick up with the next problem on Wednesday which is the same problem we just did. This is exactly the same problem we just did a minute ago. The 0 at -3, -1, 1, and 3. So this one we actually just did. We don't really need to do this again. So when we come in on Wednesday, we'll start with this question as a little review.